Hello students, and welcome to today's chemistry class for SS1. In today's lesson, we are going to be taking the gas laws, but we are going to take part 2. So let's take a look at our lesson objectives. At the end of this lesson, the students should be able to state Gay-Lussac's law on pressure and temperature, state the general gas equation, state Dalton's law of partial pressure. Let's now take a quick example. Example 1. Find the final pressure of gas at 150 Kelvin if the pressure of gas is 210 mm mercury at 120 Kelvin if the volume remains constant. Now take a look at the solution. As usual, we bring out our data. T2 is 150 Kelvin, P2 is unknown, P1 is 210 mm mercury, while T1 is 120 Kelvin. Now, using our formula, P1 over T1 equals P2 over T2, making P2 subject of the formula. If we input our figures and do the evaluation, you will see that P2 is 263 mm mercury. Example 2. A cylinder contains a gas which has a pressure of 125 mm mercury at a temperature of 200 Kelvin. Find the temperature of the gas which has a pressure of 100 mm mercury if the volume remains constant. Solution. P1 is equal to 125 mm mercury, T1 is 200 Kelvin, T2 is unknown, while P2 is 100 mm mercury. Of course, using our formula, P1 over T1 equals P2 over T2, making T2 subject to the formula. If we input our figures, we are going to have 160 Kelvin as the value for T2. The general gas equation. The volume of a given amount of gas is proportional to the ratio of its Kelvin temperature and its temperature. Now, we can combine everything we have on one proportion. I'm referring to Charles' law and Boyle's law. So now, to combine both of them, you will see Boyle's law is volume is equal to is inversely proportional to pressure, while for Charles' law, the volume is directly proportional to temperature. To combine both of them, we're going to multiply the two equations. Now, multiplying both of them, you will see that volume is equal to 1 over P times the temperature. Now, so that in the end, PV is equal to T, or we're going to have PV divided by T is a constant, meaning that P1 V1 divided by T1 is equal to P2 V2 divided by T2. This is to enable us compare two different scenarios of pressure, volume and temperature. So let's take a quick example. Example 1. 500 dm cube of a gas is prepared at 1 millimeter mercury and 200 degrees Celsius. The gas is placed in a tank under high pressure. When the tank cools to 20 degrees Celsius, the pressure of the gas is 300 millimeter mercury. What is the volume of the gas? So let's look at the solution now. V1 is 500 dm cubed. P1 is 1 millimeter mercury. T1 is 200 degrees Celsius, which we're going to convert to Kelvin by adding 273. T2 is 20 degrees Celsius. Of course, we convert to Kelvin by adding 273 again. P2 is 30 millimeter mercury, while V2 is unknown. So using the formula P1 V1 divided by T1 equals to P2 V2 divided by T2. We make V2 the subject of the formula since that is the unknown. Then we impute all the figures appropriately. After the evaluation, V2 is 10.3 dm cubed. Example 2. What is the final volume of a 400 cm cube gas sample that is subjected to a temperature change from 22 degrees Celsius to 20 degrees Celsius and a pressure change from 760 millimeter mercury to 360 millimeter mercury? Solution. First, we bring out our data. V2 is unknown. V1 is 400 cm cubed. T1 is 22 degrees Celsius, which we convert to Kelvin, while T2 is 30 degrees Celsius. Of course, we convert to Kelvin by adding 273. P1 is 760 millimeter mercury, while P2 is 360 millimeter mercury. Using our formula P1 V1 all over T1 is equal to P2 V2 all over T2. We make V2 subject of the formula, then impute our figures appropriately. If you take your evaluation, the new volume V2 will be 867 cm cubed. Let's now take a look at Dalton's law of partial pressure. This law states that the total pressure P exerted by a mixture of gases, say A, B, C, and D, is equal to the sum of the partial pressures of each constituent, provided that the gases would not chemically react together. Now, what this means is, if you have a mixture of different gases, let's say 4 gases A, B, C, and D, all in a container, their total pressure is the addition of the partial pressure of each of them. That is, what amount of pressure is gas A exerting, what amount of pressure is gas B exerting. Same for C and D. If you get each of the values, add them together, that will give you the total pressure of the gas in the container. Let's now take an example. 30 grams of nitrogen, 50 grams of hydrogen, and 10 grams of chlorine were mixed together in a container. Their total pressure was found to be 2572 millimeter mercury. Calculate the partial pressure of each of the gases. So now we are going to start this calculation by calculating the number of moles of each of the elements present. So number of moles for nitrogen would be its mass divided by the molar mass. That will give us 30 divided by 28, that's 1.07 moles. That for hydrogen would give us 50 divided by 2. Don't forget, hydrogen has a mass of 1, but because it comes as H2, so the mass now becomes 2. So 50 divided by 2, that will give us 25 moles. Then of course we take that of chlorine. Chlorine is 35.5, but because it comes as Cl2, it will be 71. That will be 10 divided by 71. That will give us 0.14 moles. So now we have the number of moles of each of the elements present. Now if we add them together to know the total number of moles of all the elements in the container, we are going to have 1.07 plus 25 plus 0.14. That will give us 26.21 moles of gases in the container. Going forward, we are now going to calculate the partial pressure of each of the gases. So for nitrogen, we are going to have the number of moles of nitrogen, which is 1.07. We'll divide it by the total number of moles of all the gases in the container times the total pressure. That will give us 105 millimeter mercury. That is the partial pressure of nitrogen. That for hydrogen, we will repeat the same thing. We'll take the number of moles for hydrogen divided by the total number of moles, which is 26.21, times the total volume. That partial pressure for hydrogen will become 2453 millimeter mercury. And then we'll repeat the same for chlorine. 0.14 divided by 26.21 times the total pressure, which is 2572. That will give us 14 millimeter mercury as the partial pressure for chlorine. Now, one way you can test to see if you are correct is you take the partial pressure for nitrogen, that for hydrogen, and that for chlorine. If you add them all up, it is supposed to sum up to the total pressure which was given in the question, which is 2572 millimeter mercury. All right, it's now time for us to take a look at the ideal gas law. The ideal gas, or the perfect gas, is the theoretical substance that helps to establish the relationship of four gas variables. We are referring to pressure, volume, the amount of gas, and the temperature. So we are looking at these four variables and how they relate with one another. Some assumptions were made for the ideal gas equation to come up. Now, those assumptions say, number one, that gas molecules are in motion and move randomly. Number two, each time the gas particles collide, kinetic energy is conserved. This is called elasticity. In some books, you'll be told that collision of gas particles is perfectly elastic. And what that simply means is that when the gas particles collide, they do not lose energy. The volume of the molecules of gas is negligible. This means that considering the volume that the gas is occupying, because it has spread all over the whole container, if we bring the whole gas particles together one by one, bring them together, the new volume that they will occupy compared to where they occupied initially when they were allowed to spread, that the new place they will occupy will be negligible, will be very small. Now the fourth one says gases do not attract or repel other gas molecules. Yes, sometimes it can be stated as force of attraction and repulsion between gas particles is negligible. Now the fifth one says that the kinetic energy of a gas is directly proportional to its temperature in Kelvin and is the same for all gases at the same temperature. Now all these five assumptions were the things that brought about the ideal gas equation. So an ideal gas will have all these five properties. So now you see that those five properties mentioned of an ideal gas, in reality most gases found in nature do not meet all of these qualifications for an ideal gas. However, they follow the rules closely enough that we can still use all of the equations above in theory, and it will not present a significant difference from what occurs in nature. This is the main reason, because you see, ideal gases do not exist, but real gases exist. So the reason why, after stating a particular law, they will tell you provided temperature or pressure or volume or whatever, they will mention a particular variable that needs to be constant, is because real gases deviate from these assumptions. But well, for ideal gases, because they don't even exist, we still hold those assumptions. So going forward, from the ideal gas statement, it means that pressure times volume can be equal to nRT, where n is the number of moles of the gas and R is a constant called a universal gas constant. We can now take an example to illustrate this. At 655 mm mercury and 25 degrees Celsius, a sample of chlorine gas has volume of 750 cm cubed. How many moles of chlorine gas are there at this condition? Now, let's take a look at the solution. Pressure is 655 mm mercury. Temperature is 25 degrees Celsius, which of course we're going to convert to Kelvin. The volume is 750 cm cubed, which we convert to dm cubed. It now becomes 0.75 dm cubed. The amount n is unknown. The R is 0.0 is a constant, actually 0.0821 dm cubed atmospheres per mole Kelvin. That's why if you notice the pressure above, we have to convert it from millimeter mercury to atmospheres. Now the final solution, n is equal to PV divided by RT. That's making n the subject of the formula from our initial equation. N will now become, so we now impute the figures appropriately, and after taking the proper evaluation, you will see that n is equal to 0.026 moles. So let's take a quick summary of what we have done. In this lesson, we have learnt about Gay-Lussac's law, general gas equation, Dalton's law of partial pressure, and then the ideal gas equation. So at this point, we have come to the end of the lesson. Thanks for watching, and hope to see you in the next class.